Okay, this is Tanner Volek. Go ahead.
Okay, so what I've done this semester is I've been testing different solvents and their ability to clean different soils off of microscope slides.
Mm-hmm.
One of the first soils I tested was...
You're leaving me behind a second.
Oh.
Okay, here we go.
You go.
Yeah.
The first soil I tested was industrial sharpie. What I did was I marked a microscope slide on the frosted end of the microscope slide and tested 28 different solvents on it. I used Image J to compare those, how well they cleaned it off, to a constant, which was just a brand new microscope slide. And with that, I gave each solvent a score and used that to find interaction spheres for industrial sharpie.
Okay.
I found two main spheres of interaction. So one of them...
How did you decide on two spheres?
Oh yeah, so when I scored the solvents, I found that there was two main groupings. One grouping was, well...
You just couldn't fit them all in one sphere?
Yeah. I tried to fit them all in one sphere, but they wouldn't all fit. Mm-hmm. I tried making a smaller sphere and then adding another solvent into the sphere and expanding the size of the sphere until the other solvent fit. Mm-hmm. But most of the time, whenever I tried to add a different solvent, a bad solvent would fit into the sphere first. Okay. So then I knew that it wasn't part of that group.
Yeah.
So then I used Povray to create a diagram of it. So this is what I created with Povray. Nice. You can see this is the first sphere. So we have methanol, ethanol, ethylene glycol, monopropyl ether, DMF. And so I have the first sphere all in blue, and all the bad solvents are in red. And then you can see down here there's green spheres. Those are part of the second sphere, which is shown right here.
Okay.
And you can see there's bad solvents in between the good sphere and the bad, or in between the two spheres. There's bad solvents. So I know that those two groupings are... Yeah,
they're not exactly in between, but you can't, if you try to fit all of those in, the sphere will be too big and get the ones on the side, like IPA, octanol, DMSO,
And then there's two solvents, propylene carbonate and chloroform, that didn't fit into either sphere.
Yeah, that's so strange.
And they didn't fit in one sphere together.
Yeah.
Because they're on opposite sides.
That's so weird.
So, but they cleaned the Sharpie off of the slide pretty well.
That's amazing. I haven't found a use for propylene carbonate. It's a great location, enhances solubility space, but I mean, it just doesn't play nice, and I'm surprised that it worked. Yeah. But that's good.
And cleaning the Sharpie off, it was pretty clear that when it cleaned it off, the bad solvents would basically not touch it.
Yeah.
And then all the good solvents that I have here, they would clean it perfectly.
That's good. So if it's in this diagrams, if it's a clean solvent, it's going to clean it down to the glass and get it off.
Yeah. And so the second soil I tested was pink Sharpie, a different type of Sharpie.
Can I ask you why you were using Sharpie? I mean, I know I told you, but
yeah.
Do you know?
Well, I know that we kind of talked about the components of Sharpie. Like
I mean, it's got like a carbon black component, which is like soot, so similar to soot. It's got a polymer binder, which is like a cooked soil. So even though it's a Sharpie and people may not have that as their soil, it represents a sticky, sooty soil that's nearly impossible to remove. Yeah. Well, we see that with a solvent, it's not nearly impossible, but with ultrasound, it's pretty tricky.
I mean, also on those frosted glass sides, it gets everywhere in them.
It gets in those frosted glasses, so that's the difficult part too, is a rough surface. Right. So we have a rough part with a sooty, sticky soil. And so that makes it a really good soil, even though people say, well, I don't clean Sharpie off my parts. You clean sticky, carbony, black stuff off your parts? Yes, well then Sharpie's a good substitute.
Right. Paint Sharpie was similar. I think it just has a different solvent. for the
Yes.
ink.
Which I thought it might have a different binder. If
Yeah.
it has a different solvent, it might have a different polymer binder, which might be more difficult to remove. So, go ahead.
I found that it was pretty similar to industrial Sharpie. There were a few differences, but I basically went through the same process.
Yes. Okay.
And I found 2 different spheres again.
Okay.
So here's the first sphere. It's pretty similar to the first sphere. The only difference is DMF isn't included on this one. And then here's the second sphere. Again, it's really similar, except this time chloroform was able to fit inside the sphere.
Okay.
And
it doesn't look like propylene carbonate did its job.
Propylene carbonate did not clean the paint Sharpie out. But this time, MEK, methyl ethyl ketone, was able to clean off the paint Sharpie. It wasn't able to clean off the industrial Sharpie, but it is one of those solvents that just couldn't fit in either of the spheres.
Yeah.
And you can see in propyl bromide, it's right there blocking MEK from being in the sphere.
Yeah, so we have propyl bromide and TCE, and we have that. Did you ever try the
death solvent?
The death the death solvent. Now it's on tape. We have a mixture of MPB and TCE that we accidentally made by taking one of them out of the degreaser and putting them into the other container. So we have this blend of NPB and TCE that might clean the Sharpie.
I tried it. It didn't do anything.
It didn't do it. Okay, so then it must be below the sphere too much to clean. Okay.
Yeah. You would think it would. I think maybe it's the proportions of it.
Yeah, it could be the proportions.
So, I don't remember which one it's mostly of. I think maybe NPB.
Yeah. That's it. Okay.
But so that's the model for paint Sharpie.
Okay.
And then I'm still working on this. I took Ethan's APA's grease data, and I made a model for that in the program. For APA's grease, there's only one sphere, and
okay, very good.
It's in a similar spot to the industrial Sharpie sphere, but in this case, it includes PCBTF. It does include TCE.
Yes.
Since it's right next to chloroform.
For the video, it's perichlorobenzotrifluoride. It's a drop-in replacement for toluene.
Chloroform, TCE.
Dichloromethane, DCM.
DCM, dichloromethane, and propyl bromide. They're all in the sphere there. And this is the only sphere for APs and grease. So.
Okay, which is just a high vacuum grease. It's a hydrocarbon high vacuum grease, which may or may not have silica filler. I don't know. We were talking about that. Yeah. So.
Well, they mentioned a lot with like what I could find with lithium greases.
Okay.
Because with silica, it's typically added to lubrication greases.
Interesting.
And a lot of the times, I have it on like the Word document I sent you.
Okay.
At some points. I don't know if it was automotive greases, but they use it a lot in that. And then also, if it's like a thermal grease, typically they use a silica polymer because it's like thermally stable.
Yes, like these silicon cookware things. I mean, they go up easily up, and temperatures are no problem.
Yeah, and they've done like I found like research papers where they added like silica nanoparticles to certain lithium greases and it like decreased the friction in the grease, so it's present.
I see. So this we thought it was the spectrum of glass, but it might be the glass particles in the grease that were giving us the ramen. That's more on the ramen later. Teaser. So that's the chromatography.
Those are So I did a little chromatography.
That's just beautiful.
It looks pretty cool.
Yeah.
So this one was with. I did one with industrial Sharpie and then just a regular Sharpie.
Yeah.
And I think let's see. The two in the middle are industrial Sharpie.
The two in the middle of what? In the panel?
In the four panel.
Industrial Sharpie.
So the two in the middle and the 4-panel one are industrial Sharpie. The two on the outside are regular Sharpie. I tried them with ethanol and then I tried them with cyclohexane.
Is that cyclohexane or cyclohexanone?
Or cyclohexanone.
Okay.
Yeah.
Yeah, it's got a ketone in it.
Yeah.
Okay.
because both of them, I chose them out of the solvents
Yes.
that worked.
Pretty dramatic differences in those chromatography.
You can see that cyclohexanone carried a different pigment.
Yes, it really
than,
did. Yeah.
The ethanol did. And you can also see the industrial Sharpie and regular Sharpie, they have different pigments in them.
They do. Yeah, that's amazing.
Which is interesting because they look the same. So, and then I found that cyclohexanone was fluorescent, so that's when we started getting into whether our solvents were contaminated.
Sure. Oh yeah, that's right. So where's the fluorescence there?
It's like right here.
You point with the mouse and I'll point with your mouth. Like I'll do that too. So this area here is the fluorescent part, this band at the top.
Mm-hmm.
Okay. Now you're tell me you think that's from the Sharpie?
Well, I at first I was
this
thinking
dry?
Yeah, it's dry.
Okay, so it dries. So the cyclohexanone's gone,
Mm-hmm.
but it could be the stabilizer from the solvent that's left behind.
That was just precipitated as it
evaporated. So as the solvent evaporated, maybe the stabilizer stayed behind, or it could be from the Sharpie.
Yeah.
Yeah.
And so, well, after that, I took a UV light and shined it on all of our solvents.
Mm-hmm.
And found them.
Yes. Now, how would you
solvents.
test if this chromatography experiment was just your solvent, a fluorescent compound?
Well, I mean, I guess I could try it with different solvents.
Yeah, and no Sharpie. So you just elute it, do a blank.
Mm-hmm.
You know, elute the solvent up to the line.
Mm-hmm.
You know, you have one with the Sharpie on it, one without.
Oh yeah, well I did that. Yeah.
You did that,
Mm-hmm.
okay. Yeah.
I did that with cyclohexanone
Mm-hmm.
with just nothing,
Yes.
and yeah, I saw a little band. It was really faint, but it was small.
But there was some from the stabilizer. That's interesting.
That went all the way.
Yeah,
so.
yeah, that makes sense because it'd be soluble in that.
Right.
Yeah. All right.
Yeah, and so well, the next soil I'm using is rubber cement. I don't have a picture of it. But
Okay.
If they can see it on the webcam.
Yeah, that's right. Come on up close.
Yeah.
Let me split to Control 5 here, change scenes, and let's go to that arch.
Okay, so well, we were trying to find a way that we could test the rubber cement.
Yes.
So we tried to put it in these
The straw
in this
tanks.
beaker.
Yeah.
And have the straws be filled up a little bit with the rubber cement,
Yes.
and then it would dry.
Which we've done this before with urethanes and other things.
And it didn't work.
It didn't work because that was not.
Yeah, it just went to the bottom and then made a little.
Yeah, so the straws actually have to go all the way to the bottom.
Yeah.
And so you need to put enough in there so it gets up
Yeah.
into the straws. Yeah. So it needs to be probably
And fill
a
up
quarter inch
kind of
deep minimum.
Yeah.
You know. And do we have the blue straws? Because those are smaller.
We have one left.
Oh, see, I thought I ordered some. I'll have to look into that again.
We have a ton of green straws.
Okay, so let me look for the blue ones. Okay. All right.
Yeah.
So, let me go back to scene 1. Okay.
Yeah, and then I did some research on the flashpoint of ethanol because we were going to use it for
Just looking at ethanol water mixtures?
Yeah.
Yeah,
Mhm.
yeah.
just to see which would be like what concentration of ethanol
Yeah.
would be safe. It's a very small concentration.
Yeah, so as soon as you get above 10% ethanol, the flash
Becomes
point drops
flammable.
below 100
Yeah.
Fahrenheit, and that's classified as flammable. Yeah.
Mhm.
That's unfortunate.
So
I think still in vacuum cyclonucleation we could use it because it's a contained system.
and this is just the list of solvents that were fluorescent.
Okay, which it says contaminated, but they may not be. It may be the fluorescence of
It
an
may just-
antioxidant. So like, what is it called? It's BHT, butyl hydroxy. Butyl hydroxytoluene. Yeah, that's right. So it's a toluene molecule. Para to the methyl group is a OH. And then ortho to that OH on either side are T-butyl groups. So BHT is an antioxidant and likely to be fluorescent. It'll show up in the solvents as a fluorescent as fluorescence, which again, if it's in there as a stabilizer, it's not contamination per se. Okay.
And then I made a list of all the solvents in the lab last night.
Okay.
Your turp beetle is weird. I don't know. Something's up with
Let me go down there and see which one. What are you talking about? Let me run it again. Which one's weird?
the turp butyl solvent that we have. Turp butanol, I mean.
Yeah. Yeah, it's a tarbutyl alcohol. Yeah. Which I don't see it on.
Oh, it's not on that thing.
Oh, it's not on here. Okay.
Down in the lab when I
What's
was
weird about it?
Well, it's a solid. Well, it's like it almost looks solidified.
Really?
So it looks like a gel almost.
Oh.
And I was turning around. There's only a little bit of liquid in there, and the rest is filled up with this weird gel thing. So
Okay, we'll definitely look into that.
That would be weird.
Yeah.
Yes.
I don't know how that could
I was like, I
polymerize.
that would be weird.
How could that polymerize?
Something's in it.
Look at the melting point. You know,
Okay.
some like phenol. You know, it can be solid at room temperature, and you just roll it up to like
just put it right
29
in this.
degrees or something, and it'll melt. Yeah, so I don't know, but look up the melting point of that. That might be interesting. Okay, and then I'll stop the video.
I know on the